770 feet. This is the massive height of the Oroville Dam, which serves as a colossal barrier positioned deep within the Sierra Nevada mountains of California. Why was such a monumental structure required in this specific geological region? It would seem that a smaller earthwork could manage local rivers, but in reality, engineers needed to restrain a body of water exceeding 5 billion gallons to protect the entire downstream territory. This massive structure of concrete and rock was designed not only to store water, but also to contain floods powerful enough to devastate the region within minutes. At first glance, the dam is a static monument, but holding back water at this scale has never been simple. The project faced significant obstacles as mountain geology, extreme hydraulic pressure, and the engineering limits of the 1960s turned the construction into a challenge many believed was too risky to realize. Everything only gets more complicated when considering the sheer volume of the reservoir, which currently holds more than 1 trillion gallons of water. One can notice how the dam functions as the water lung of the entire California State Water Project, helping to regulate river flow during the spring snowmelt and preventing catastrophic flooding in the rainy season. This reservoir ensures a stable water supply for the state during the dry months. Though the process of maintaining this balance is only gaining momentum, completed in 1968, Oroville remains the tallest earth-filled dam in the United States. Heavy rainfall in early 2017 tested the structural integrity of the facility to its absolute limit as record-breaking precipitation poured into the watershed. During this period of intense stress, the main spillway of the dam failed unexpectedly. Concrete slabs with a thickness of only 20 to 25 centimeters were torn apart by the velocity of the discharge. It is visible how water seeped underneath these slabs and generated intense uplift pressure against the material. The weakened bedrock underneath the concrete eroded rapidly into a massive crater as the force of the water carved through the earth. The equipment gradually succumbed to the hydraulic forces, and the primary overflow channel became a source of immediate danger. Transition to the next level of the crisis occurred as the erosion threatened to undermine the entire control structure. The process of stabilization began immediately after the crisis, as the material was prepared for an emergency reconstruction of the damaged zones. The flow of water continues to be monitored as the structure prepares for the next phase of its technical life. 2017 was the year the state initiated a massive reconstruction project to restore the integrity of the hydraulic system. The first phase of repairs launched in May of that year. Why was the timeline for the initial stage restricted to only a few months? Completion was required by the end of December to ensure the structure could withstand the pressure of the next rainy season. By the end of 2018, engineers had fully rebuilt the entire spillway system, encompassing both the primary and emergency structures. Fractured concrete sections and the weakened foundation remaining after the incident were the first priorities for the repair crews. One can notice how the equipment gradually strips away the damaged material to reveal the underlying layers. Construction teams had to remove over 1,000 meters of the spillway. It only looks obvious to clear the path, but this required the extraction of tens of thousands of tons of concrete using excavators and hydraulic breakers. Blades and drill bits rotate ceaselessly during the preparation of the site. Everything only gets more complicated as the work moves onto the incline. This phase lasted several weeks because the slope of 35 to 40 degrees made it extremely difficult for heavy machinery to maneuver safely. The process is only gaining momentum. Hydraulic breakers shatter the old concrete layer while workers constantly spray water over the work zone. This prevents fine dust from spreading into the air and clogging the machinery. The liquid also cools the breaker tips and stops fragments from flying off dangerously. One can notice how the water flows down the steep surface, keeping the removal work controlled. But in reality, some concrete sections remained resistant to standard mechanical force despite appearing undamaged. The internal steel reinforcement made these areas nearly impossible for excavators to penetrate. To overcome this, the crew drilled hundreds of small holes in a dense grid pattern. Low-charge explosives and detonators were placed into each opening with precise measurements, but this is just the beginning. Wiring for the charges is connected by hand and inspected to ensure a uniform trigger. Transition to the next level occurs once the area is cleared. When activated, the controlled explosions fracture the concrete along intended lines. One can notice the dust settling in slow clouds as the sections are peeled away. This method ensures the remaining material is removed without harming the bedrock underneath. The material is ready to move to the next processing phase without haste. 21 cubic yards of roller compacted concrete are loaded into the bed of a heavy-duty dump truck every 5 minutes at the central mixing station. Why is this specific dry mixture of cement, gravel, and sand chosen for the foundation? High-strength roller compacted concrete, or RCC, is engineered specifically for massive industrial structures that require extreme durability and load-bearing capacity. The process is only gaining momentum. After the filling cycle, the truck is immediately dispatched to the construction zone located on the steep mountainside. One can notice how the dump truck maneuvers on the incline before lifting its hydraulic bed to release the material onto the spillway surface. The loose RCC forms a thick raw layer that is spread into long continuous strips running parallel to the spillway channel. Bulldozers follow the trucks without delay to level the mix and adjust the width, slope, and elevation. It is visible how the equipment maintains centimeter-level precision to ensure the foundation bonds tightly to the natural terrain. But this is just the beginning. High-tonnage vibrating rollers make multiple passes over the strips to compact the material. The loose mixture is transformed into a dense, solid concrete mass that locks firmly to the underlying bedrock. It seems simple at first glance, but this cycle of placing, grading, and compacting must be repeated continuously, layer by layer. The process continues until the new foundation reaches the required thickness and hardness specifications. Workers spray a thin film of water over the surface to keep it moist and activate the chemical hydration process of the cement. Everything only gets more complicated as a specialized leveling attachment mounted to the boom of an excavator begins its operation. The wide leveling blade is lowered onto the surface and moved back and forth with a steady rhythm. The equipment gradually shaves down high spots and fills in low areas to create a continuous plane that matches the design slope. One can notice the accuracy of the hydraulic controls and precision sensors, which maintain tolerances down to a single millimeter. The crew simultaneously presses rebar dowels into marked positions across the surface. These metal elements prepare the foundation for the structural concrete layer that will eventually be placed on top. Transition to the next level. Inspectors use laser levels to scan the entire area, verifying that the elevation and flatness meet the engineering requirements. The material is ready to move to the next processing phase without haste. 100% of the spillway surface is shielded by a dense grid of green epoxy-coated rebar. Why is this specific specialized coating applied to every single steel rod? Standard steel would quickly succumb to oxidation in an environment defined by high-velocity water flow, so this chemical barrier is mandatory to ensure structural longevity. The construction team lifts each individual bar into position with mechanical precision. The process of reinforcement begins with the placement of small concrete spacers. These blocks serve a critical function by maintaining the exact elevation required for the steel skeleton. Workers tie the rods together to form a perfectly uniform square grid that spans the entire width of the structure. In complex sections where the floor meets vertical walls or exposed rock, the bars are bent manually to follow the natural contours of the terrain. This technique ensures that the anchorage is secure and the structural connection remains seamless across every square inch of the spillway. Efficiency is maintained through the use of massive pre-welded rebar panels. These heavy modules are fabricated at an off-site facility and then transported to the edge of the spillway. One can notice how a heavy-duty crane lowers these pre-assembled grids into position, significantly accelerating the installation phase compared to manual assembly. Once the grid is fully secured, it forms a rigid structural skeleton capable of supporting immense hydraulic loads. But this is just the beginning. The logistics of the concrete phase involve a continuous cycle of machinery. Concrete trucks receive their loads directly from the mixing plant, where a specific thermal management process occurs. Liquid nitrogen is injected into the fresh mixture to lower its internal temperature. This cooling is necessary because the intense heat of the California climate could cause the concrete to overheat and crack before it fully sets. One can notice the white vapor of the nitrogen as the temperature is stabilized to exact specifications. The vehicles move in a non-stop queue toward the base of the massive structure. From there, the trucks must climb a steep ramp to reach the active work zone, maintaining a pace that matches the daily pouring schedule. At the summit, a chute or a specialized pump line extends across the green rebar to discharge the heavy batch of wet concrete. it is visible how the gray material flows over the epoxy-coated steel, beginning the final layer of the spillway surface. Air pockets are eliminated through the use of high-frequency internal and surface vibrators. These mechanical tools force the concrete to settle into every gap around the reinforcement bars, creating a solid bond with the roller-compacted concrete foundation below. The resulting surface slab measures between 12 and 18 inches in thickness. This density is calculated to withstand the massive pressure of water releases. The process is only gaining momentum. Operations continue from the first light of dawn until well after nightfall. A constant flow of material is required because any significant pause would lead to the formation of cold joints. These gaps act as structural weaknesses that could fail under stress, so the pouring must remain a continuous, unbroken event. Section by section, the slab grows across the foundation, creating a high-strength shield for the spillway. Workers utilize long screed bars to pull and spread the thick mixture evenly. The camera glides along the wet surface as the tools level the concrete to a uniform grade. This ensures that no low spots or areas with insufficient material remain to disrupt the hydraulic flow. At first glance, the leveling seems like a simple manual task, but in reality, it determines the final smoothness and durability of the entire engineering project. The material is ready to move to the next processing phase without haste. Two manual leveling tools move rhythmically along the form edges to ensure the concrete reaches the exact design elevation. Why is such a high degree of precision necessary during the initial leveling phase? It only looks obvious to smooth the material, but in reality, any deviation in height creates uneven flow dynamics across the spillway surface. Power trowels and hand tools follow the initial adjustment to create a uniform texture while lightly compacting the top layer of the fresh mixture. This finishing sequence is not just for aesthetics, as it forces out surface air bubbles to form a dense and durable structural skin. One can notice how the crew transitions from finishing the tight corners by hand to deploying automated equipment for the larger surface areas. The process is only gaining momentum. Automated rolling machines are brought in and guided along specialized rail systems to flatten the concrete while the material remains workable. These heavy rollers exert downward pressure while simultaneously vibrating the mass to eliminate internal voids and densify the concrete in a single pass. It is visible how the pour and finish as you go method allows the team to increase production speed without sacrificing the quality of the final surface. After the roller-compacted concrete layer has dried and reached sufficient structural strength over a period of 1 to 2 days, the construction team begins the next critical phase. High-power saws are utilized to cut expansion joints across the hardened surface with mathematical accuracy. These deep incisions allow the massive concrete slabs to expand and contract during temperature fluctuations without the risk of uncontrolled cracking. This is especially vital for a spillway stretching over several hundred meters in length. But this is just the beginning of the structural protection. Workers install subsurface drainage pipes in their designated positions beneath the concrete layer. At first glance, these pipes seem like minor additions, but in reality, they prevent water from building up and creating dangerous upward pressure on the spillway. One can notice the team filling the areas around the pipes with treated soil and rocks to secure the drainage system against mechanical damage. The material is ready to move to the next processing phase without haste. 55,000 feet of drainage pipes comprise the foundational network of this hydraulic system. Why is such an extensive length of piping necessary beneath the surface? It would seem that a smaller volume could handle the runoff, but without this precise density of drainage, the sheer pressure of groundwater would eventually compromise the structural integrity of the entire spillway. If one were to stack these pipes vertically, their combined height would stretch over 10 miles into the atmosphere. The process is only gaining momentum. Heavy cranes begin the task of hoisting massive reinforcing steel panels into the air. These green epoxy-coated rebar structures are pre-tied on the ground to ensure every intersection meets technical specifications before being lifted. The camera glides along the edges of the spillway as the steel is set precisely into its designated position. It only looks obvious to place steel in a trench, but in reality, the alignment must be perfect to counteract future hydraulic forces. Workers immediately connect each panel using a combination of wire ties and heavy steel plates. This creates a continuous, heavily reinforced wall structure designed to withstand the extreme pressure occurring during high-flow releases. Everything only gets more complicated. Temporary bracing is installed with the hiss of pneumatic tools to keep the steel framework stable. This prevents any shifting or warping of the rebar skeleton while it awaits the weight of the wet mixture. Once the entire reinforcement system is secured, the crew transitions to the next level of construction. One can notice the arrival of steel formwork panels that enclose the rebar. These molds define the final shape and thickness of the spillway walls. High pressure lines are connected to the mixing plant, and fresh concrete begins to flow continuously into the narrow space between the forms. The equipment gradually encases the entire steel structure in a gray, viscous mass. During the pour, workers use internal vibrators that submerge into the wet mixture. The boulders of aggregate shift as the vibration consolidates the concrete, ensuring it fills every void and eliminates trapped air. This removal of oxygen is a critical factor for achieving the density and long-term strength required for water infrastructure. It gets more complex further on. The wall is poured in distinct lifts, allowing for careful management of the liquid pressure against the forms. Engineers check each layer for proper elevation and vertical alignment using a high-precision laser system. One can notice the red beam of the laser cutting through the dust to mark the exact design height. When the concrete reaches the top of the mold, the surface is troweled smooth by hand to create a clean, uniform edge. The equipment is then cleared from the area, and the wall is left in place for several days to undergo the chemical process of curing. The formwork is only removed once the material has achieved sufficient structural hardness. The transformation of the spillway moves to the next phase of processing. 35 meters per second is the speed water reaches as it hurtles toward the terminal section of the spillway. Why must engineers install massive concrete teeth at the very base of this structure? One can notice how the water does not simply flow into the river, but instead crashes against energy dissipation blocks designed to redirect and decelerate the torrent. But this is just the beginning. These energy dissipation blocks consist entirely of reinforced concrete, cast to absorb extreme impact forces. The structures function by breaking the uniform flow into chaotic, dispersed streams, preventing the water from carving into the riverbed. It is visible how the massive blocks stand firm against the hydraulic pressure that would otherwise erode the entire foundation. It seems simple to reinforce a spillway, but in reality, the scale of the emergency overflow area requires a different engineering approach. The construction team transitioned from the main chute to the emergency spillway, utilizing the roller-compacted concrete method across a significantly larger territory. Heavy-duty trucks move in a continuous cycle, hauling dozens of tons of material to the base of the site, where they deposit it in precise, thin layers. Each lift of material measures between 8 and 12 inches in thickness. Bulldozers maneuver across the surface to level the mixture, followed immediately by vibrating rollers that compact the concrete into a dense, solid mass. One can notice how the natural hillside, once composed of loose earth and vegetation, is slowly transformed into a massive, erosion-resistant platform. The process is only gaining momentum. This repetitive cycle occurred hundreds of times to ensure the structural integrity of the splash pad. The resulting concrete surface covers an area equivalent to 25 football fields, providing a shield against the weight of billions of gallons of water during a flood event. Because of this roller-compacted reinforcement, the slope can now withstand overflow without the risk of severe failure. The reinforced emergency spillway remains a stable, permanent feature of the landscape, ready to manage hydraulic loads that once caused catastrophic erosion. The material is ready to move to the next processing phase without haste. 600 workers completed the entire repair process after laboring without interruption for more than 200 days. This massive engineering effort operated 24 hours a day, 7 days a week, specifically to meet the critical deadline of the rainy season in California. But was the structural integrity of the massive concrete assembly truly ready for the force of millions of gallons of water? It seems simple to assume the concrete would hold, but in reality, only a live trial under pressure can confirm the calculations of the design team. The operations team initiated a test release once every individual component was inspected and certified to meet the established standards. Engineers released the first flow of water down the spillway at discharge rates that increased gradually over several hours. one can notice how the water gains velocity as it descends the steep incline. The camera glides along the concrete surface, sidewalls, and the energy dissipation blocks located at the terminal end, allowing for a detailed observation of structural stability under load. Everything only gets more complicated as the volume of the discharge rises. Sensor arrays installed at strategic intervals along the spillway structure continuously recorded vibration levels, physical movement, and internal water pressure. These instruments ensure that the entire system behaves exactly as designed by the engineering team. It is visible how the water creates a white, turbulent foam as it strikes the dissipation blocks, converting kinetic energy into heat and sound. The new spillway was officially declared safe and ready for full operation only after the flow reached its maximum test load, without a single sign of distress or structural anomaly. The equipment gradually powers down as the test concludes successfully. This marks the transition to the final operational status of the infrastructure. All information regarding these technical processes was compiled from multiple specialized engineering sources. The repair of the massive structure concludes this phase, opening the road to long-term regional water management. Thus, the engineering project reaches the standard ready for the next decade of service.